Good afternoon to all of you. So, in the last lecture, we were discussing at the end of the lecture this example. So, if X is any set, and if we define this collection T infinity, then whether it is a topology or not. So, I think some of you have given the answer. So, in this case, if we take X equal to, let us say, set of natural numbers, and we are defining T infinity on this set of natural numbers as the subset of n, so that either u equal to phi, u equal to x, that means u equal to n, or u complement is an infinite set. So this is the example, and we need to check that this example forms a topology or not. So what will be the basic examples in tau infinity? So clearly phi and set of natural numbers will be in tau infinity, right? Because of these two conditions. And if I take singleton 1, then it is in tau infinity. Why? Because the complement of 1 is 2, 3, 4, all these numbers. So set of natural numbers minus singleton 1. So that is 2, 3, 4, all these numbers. So this is an infinite set. Right? So therefore 1 belongs to tau infinity. Similarly, singleton 2, singleton 3, all these elements belongs to tau infinity. So actually we should write tau infinity of n, because we are basically taking x equal to n. Right. So all the singleton sets belongs to tau infinity. And if so, let us assume that suppose tau infinity is a topology on x equal to n. So if it is a topology, then we know that it is closed under arbitrary union. So suppose this is true, if it is a topology. So if it is a topology, then we know that all these sets belongs to tau infinity. That means union n equal to 2 to infinity n. So that is basically the set 2, 3, so on, 2, 3, 4, so on. So this, if it is a topology, it should belong to tau infinity, right? So let us call this set U. So therefore, U defined to be this set belongs to tau infinity. But does this set belongs to tau infinity? 2, 3, 4, no. It is not, right? Because why? Because its complement is in the set of natural number is a finite set. So this is a contradiction. What is the contradiction? Contradiction is that the complement of this, uh, simply we write U complement. So U complement is singleton 1, which is a finite set. Right, so this is what we already discussed in last lecture. Some of the students have mentioned this thing. Uh, so just revising that. So therefore, this is not topology on the set of natural number, and therefore on the general set, for any general set, this is not true. We are not saying for every set this is not true. We are saying for x equal to n this is not true. That means in general this is not topology for a general set x. Okay, so this is regarding that example. Now, what we discussed in the last lecture, let me revise once and then I will, we shall go further. So last lecture we discussed subspace topology. So like every vector space, we can find some of the example of a subspace. Like R2 has a subspace which is a x-axis. So the same way here, if I have a topology tau on a set X, tau on a set X, and if I know that Y is a set which is subset of X, on which we already know some topology on X, then using this topology I can define topology on Y. So that is the subspace. So how do we define that family? We just take intersection with Y all the open set in X. That means elements of tau. So this collection of U intersection Y forms the subsets of Y, and that we have already verified it is a topology on Y in the previous lecture. So it is closed under finite intersection and arbitrary union, and phi and Y belongs to this family. So if I have a Y is a subset of X, then whatever topology on X, I can use the elements of that topology to get the elements of the topology on Y. And we have seen two examples that if I define discrete topology on X, then the subspace topology on Y is nothing but the power set of Y. That means it is a discrete topology. And I have given this as an exercise so that you will get more clear picture of this example. And if I have a standard topology on R, and if I consider Z as a subset of R, then on Z, by the definition of subspace topology, we will get this definition. This is the definition of subspace topology on Z coming from R, and that we have verified it is nothing but the collection of all subsets of Z. And whenever topology is equal to the collection of all subsets of the set, that means the topology is discrete topology. So briefly, what we proved in this example is, if I take on R the standard topology and I, I, I use it to define subspace topology on Z, then that subspace topology is nothing but the discrete topology on Z. That means the elements of tau Z are all the subsets of X, all the subsets of Z. So This is what we have discussed yesterday, and then we discussed basis. So using basis of x, I can get basis of y, basis of the subspace y. What is y? Y is a subset of x on which we can define the topology in the using the previous definition tau y. And for tau y, what is the basis? Uh, basis is this one. So in this lemma we verified that by is a basis for the subspace topology. Okay. So what is today we want to discuss is we already know that if I have a basis, then I can get a topology generated by that basis, right? So is there any way to get a basis? So there is one notion, small notion, it is called the subbasis. A subbasis S for a topology on X is a collection of subsets of X whose union is the whole set X. So what is a subbasis? Subbasis is a collection of some subsets of X. The union of those subsets is the whole set X. So we shall see some example later on. So this definition of subbasis, and every subbase gives us a basis which we shall denote by S1 intersection S2 intersection Sn, where S1 S2 Sn belongs to S. So in other words, what is this? This is the set of all finite intersections of elements of S, right? So when this means whenever I will take S1 S2 Sn n elements in S, the intersection of those n elements is known as the finite intersection of elements of S, and all such intersections belongs to this family. So here I am claiming that it is a basis for this set X. So let us verify that. So proposition or lemma, whatever you call it, show that S is a basis on X. Sorry, not S, BS. And we can specify here where what is S. S is a subbasis for x. So proof. So did you understand what is the basis? What is the subbasis? Definition of subbasis. Okay, so uh, since, let me explain again. So what is subbasis? Subbasis is a collection of subsets of X. Let us denote it by S alpha, right? So S alpha are basically subsets of X. So what when this family is called a subbasis if union S alpha is X, right? So the set of elements of S, its union is the whole set X. Then we call such a family as to be the subbasis, right? So these are, just remember this condition. Otherwise, let us write down. Uh, okay, so S let S defined to be collection of S alpha be a subbasis for X, for set X. So that means what? That means union alpha S alpha is X, right? Anyway, we'll use this. So this does not, by coming by definition, we want to prove that the family Bs, which is a union of the elements S1, S2, Sn. So if you confuse this notation S alpha, you can use, otherwise I can use Si also for more better understanding, because here I'm mentioning S1, S2, Sn. So better notation is Si. So Si belongs to S for every I. So what are the properties? What properties we need to check for the basis? First,
So I think it's S1 intersection S2 intersection S3
yes, so you're right. So we have to take the intersection. So I think earlier I mentioned correctly. Okay. Okay, thank you for the correction. Now, what are the properties we need to check for that this is a basis for X, this family. So first condition of basis is that for every element X in X, there exists a basis element B in this family such that X belongs to that, right? So now elements of V are of this form. So that means for every X, small x in this set, we need to show that there exists some such element which contains that X. So let, for the first property of basis, let X belongs to X. We need to find some element of this family which contains X. So can we always find such element? We need to use this definition of the subbasis. So since x belongs to x, can I say there exists Si in S such that x belongs to Si?
Yes, sir. Yes, sir.
How we can say that? What is
Because
the
X is union of SI, na?
yes, union of Si is x. So that means if I take any element of x, that means there exists some Si which contains that x. And the finite intersection of Si. So if you confuse, I can also denote by Sj, because now there is some I already I use, so I can use Sj. So now I have single element of this family, so that also belongs to Bs, right? So single element also belongs to Bs because this is a intersection of finitely many elements of S. In particular, I can take singleton also, right? So this first property we have already proved for the basis. So is this definition clear? Bs is the set of all finite intersections of the elements of S. So this n basically is changing. So that is what I want to say. So S1 also belongs to these. S1 intersection S2 also belongs to these. S1 intersection S3 intersection S5 is also belongs to Bs, right? Because this all are the finite intersections of the elements of the family S, right? So whatever I take single set or I take intersection of two set, intersection of three set, all these sets belongs to Bs. So that is definition of the Bs. Now second condition is that if I take x belongs to B1, x belongs to B2, then there exists B3 in the basis, so that x belongs to B3 which is contained in B1 intersection B2. So let x belongs to B1. B1 means some such intersection. So that means x belongs to, let us say, S1 intersection S2 intersection Sn, right? Where S1, S2, Sn are finitely many sets of S, and let x belongs to another such elements, right? Another such element. So another such elements means n will be different and sets may also be different. So that means x belongs to, let us say, S1 dash intersection S2 dash intersection Sm dash, where S1 dash S2 dash Sm dash belongs to S. So now I hope it is clear what is the definition of Bs. We will take all such finite intersections, and n and m may be different or may be same. So these are two elements of Bs, right? Because these both are the finite intersection of elements of S. So what we need is we need to find, so what is the claim? Claim is to find element B3 in Bs. So basically it is the intersection of elements of S such that x belongs to B3 which is contained in both of these elements. right? So such a B3 we want to find, and B3 will also be of the intersection of elements of S. So let us try to prove this. The proof is proof of claim. So if I have two sets, then obviously if I want to find a set which is contained in both the set is the intersection of these two sets, right? So if I take the intersection of this these two sets, then what I will get? I will get S1 intersection S2 intersection Sn intersection. So is this element belongs to Bs?
Yes, sir.
Why? Because it is
Finite intersection.
finite intersection of elements of S,
Yes.
right? All S1, S2,
Yes, sir.
Sn, S1 dash, S2 dash, Sm dash belongs to S. So as you have said that it is element of Vs. So now using these, so let us call this element B3. This set means this set. I call it B3. So then it is clear that X is in this B3 and it is contained in both of these intersections. In fact, this relation is actually equal, but we need a subset or equal, right? So both the properties of basis is verified. So therefore, Bs is a basis on X. Okay, so this what we discussed so far. Let me revise once. So in this lecture, we defined the notion of subbasis. So subbasis is a collection of subsets of X whose union is X, the whole set X, and this subbasis gives us a basis. Now we already know if I have a basis, I will get a topology which is the union of sub elements of basis, right? So in short, if I have a subbasis, what I will do? If I have a subbasis on X, to get a topology, first I will take a collection of all finite intersections, right? And then I will take all the unions of those sets. So let me see if I can discuss one example. So let us take X equal to the set of natural numbers. So if I define singleton 1, singleton 2, complement, singleton 3 complement. So is a subbasis
Yes.
on X? So answer is yes. So why it is subbasis? Next question. If it is yes, then is what is BS? If yes, find BS and the topology generated by BS. So answer is yes, that is correct. So why this is subbasis? Because its union, if we take it the union, then the union of n complement, n belongs to n. So that is exactly the union of all these sets, right? So elements of S. So what is the union? Union is, so basically we are taking, so n complement is n minus 1. This is first set union n minus 2 union, so on. So what will be the union of all these sets? Is it set of natural numbers? Yes, it is a set of natural numbers, right? Is it clear? I hope it is clear to everyone.
You're not clearly audible.
Oh, then why you're not saying? So is this question and so just now I am not audible or earlier also?
Right now.
Okay, right now. So let me explain the example again. So let x equal to the set of natural numbers, and I'm taking S to be the family of sets. The first set is one complement, the other set is two complements, third set is singleton three complements. So I'm writing one complement means, I hope it is clear, this is n minus 1 because our x is n. The complement in the universal set x, which is n. So one complement is n minus 1, so that is basically 2, 3, 4, so on, all these integers. So that is my first set. Then I'm taking two complements, second set, third set, so on. So what is the condition of subbasis? Subbasis is its union should be X, right? The unions of elements, so all these should be subsets of X and its union should be X. So in this example, these sets one complement, two complement, three complement, you have to check its union is this set X, this set of natural numbers. So that is first condition. So when I take the union of all this set one complement, two complement, so on, I can denote in this way, right? The union of singleton n complement, n belongs to n, n belongs to set of natural numbers, and this, is it clear these two are same sets?
Yes, sir, clear.
It is clear, right? So so therefore this is a basis, S is a subbasis, basis on the set of natural numbers. Now what is BS? So BS is defined to be the finite, all finite unions of elements of S. So can you guess what will be this set? sk
Power set of n.
see let us try to verify that. So if I take what is the single set,
Finite,
it is
finite intersection.
yes, you are right. Again, I have done some mistake. It is finite intersection. So thanks for reminding again. So
N.
yeah, so let us take two sets at least, right? And let us see. So what will be this set? This is finite
N,
intersection of
n minus
N.
1, 2.
two elements. I'm not taking here union again. I'm taking only intersection.
N minus 1, comma 2.
Yes, so it is n minus 1 comma 2. Right. So here I have taken intersection of two elements of S. Suppose I take three elements, then I will get n minus those three elements, right? For example, one complement, two complement, intersection, three complement. So this is also finite intersection. So this is nothing but removing 1, 3, 5. So now can you guess what elements can I explain this thing in a simpler way? So basically I'm getting all these sets in BS. So
So
what are
sir,
the
n का तो
हाँ,
n plus 1 up to आगे चला जाएगा ये.
क्या
n plus
होगा?
1, comma n plus 1,
पावर
comma
सेट
n
ही आएगा सर.
plus 2.
पावर सेट. पावर सेट आई थिंक.
Does n belongs to BS? Is it visible? Does
No sir, I think no.
answer is no, right? Because at least we are removing. If I take single set, even in that case I am removing 1 point. If I take two sets, I am removing 2 points. If I take three sets, I am removing 3 points. If I take finitely many sets, that means I am removing finitely many points. So basically, I am taking complement of the finite set. So what will be this set? This set is all. So easily we can write as n minus a, where a is a finite set. So is it clear now what is B of S?
Yes sir.
Okay,
Yes
so
sir.
this is B of S. Now, what will be the topology generated by basis? So that is all unions of elements of the basis, right? You take all unions of the elements of basis. So we already know the complement of finite sets belongs to the
सर ये
basis.
बेसिस बनाएगा, ये भी तो कंफर्म नहीं किया अभी.
वो चेक कर लिया ना, ये तो थ्योरम ही प्रूव कर दिया पूरा कि मेरे पास अगर इफ आई हैव सब basis I can get a basis, that is this theorem.
नहीं, for this particular integral example, sorry.
We have proved in the general set X.
Okay sir, okay.
So this is a particular example. So in general case it holds, so therefore it is holding in this special case also. Here also you can verify. In fact, it will give you more idea of this proof. If you want, you can separately also verify. So now we have a basis. The question is, what is this set? The clearly all the elements of the basis will be in the topology, right? Because we are taking all the unions, so clearly this set is there. So n minus a, where a is a finite set. So this is a basis, so this is anyway subset of this set. So is there any other element than these sets here? So the question is that if I take union of all such sets, so some of you have said it is power set of n or something, right? So which subsets of n I can write as a union of such sets which does not belongs to this family? So in other words, I want to say this union n is exactly this topology. So for example, if I have the set n minus a union n minus b, so what will be this set? Is it again of this form? A and b are finite sets. So is it true? We can verify simply also. N minus 1 comma 2 union n minus 1 3 5. What is this union? N minus
Yes, sir,
n minus 1, right? So if I take finite union of such sets, then I will get n minus elements of this only. But here I have to take arbitrary union. So when I take arbitrary union, only one element will add up, which is n, right? So exactly this topology is nothing but all these basis element sets plus the set of all natural numbers.
And A and B are disjoint, then this union is basically N, sir, I think.
What you are saying? Disjoint?
A and B are disjoint, then union is N.
Then it is union is n. Correct. So if I take 1 3 union, yes, so you have given the correct example. So how we are getting n? So this will show us that n I can write as a union of two elements of the basis. So therefore this belongs to the topology. Right. So this is correct. So actually this says that n belongs to this set. Right. So this already basis element, so it belongs to topology. This is also topology. Now only thing you have to observe that there is no elements is remaining other than these two, right? So once you believe these two sets are same, that means this is the topology generated by these basis elements. Then you have to note that what is this topology? Cofinite topology on the set of natural numbers, right? Because what is cofinite topology? Complement of the finite sets belongs to that, or the full set belongs to that, right? So that is exactly this. This is a cofinite topology, and that is exactly coming from this subbasis. So for cofinite topology directly, we are not able to clearly identify what is the basis. Therefore, this notion is important of the subbasis. So it gives this simple example for the finite complement topology for the natural numbers. Okay, so I think so. Do you have any questions?